My name is Michael Weiss-Malik. It's my pleasure to bring Dr. Robert Bussard here to give a talk on alternative fusion energy. Dr. Bussard has a PhD from Princeton. He's currently functioning as co-founder and director of Energy Matter Conversion Company. He's a former assistant director to the U.S. Atomic Energy Commission and has held prominent positions at Los Alamos National Labs, Oak Ridge Labs, and TRW Systems, among some other places. So he's here to talk about his ideas and some of the results that they've recently been able to make public. So also this talk is going to be posted to Google Video, so please refrain from asking any confidential questions during the Q&A session. Please welcome Dr. Bussard.
Thank you, Michael. I'm very pleased to be here and see all of you interested in something that, if it works, would really help us a lot on this planet. As I was telling Noel Garlick earlier, I started out in the engineering R&D business 57 years ago in the spaceflight era, and rockets in space were the thing that moved me. And that's what caused me to get into frontier technology developments, which led me down this long trail to this fusion program. What I'm going to tell you about today is listed on this slide that you've surely all read by now. I want to talk about what is nuclear fusion, how is it different from fission, and where does it go, and what are its problems, and what we did in our small company. We actually named it Energy Matter Conversion Corporation because we liked the fact that Einstein had invented it, and it's EMC squared, and we have a registered trademark. What we learned from our work and the general conclusions, and then at the last, why are we doing this? What is it good for? It's not just scientific entertainment, and it's not we're not doing it to make money, we're doing it for a particular goal, which will turn out to make a lot of money, and how to get there, what the next steps have to be, the end of the trail. Thanks. Okay. We have to turn it. I'm making an assumption, which is maybe wrong, that a lot of you are not familiar with the details of fission and fusion energy because you're in the IT business, but that may be wrong, and I apologize to those of you for whom this is boring. But fusion is in fact the energy that powers everything in the universe. It's the energy that makes solar energy. Every photon that falls on the ground comes down from the sun from a fusion reactor. Fission is when heavy atoms that are basically nearly unstable split into two radioactive atoms, and fusion is when two light atoms merge into something and it splits. Fission has the property that every fission process makes a radioactive isotope that is very hazardous and dangerous, and it gives us 3 Mile Island and Chernobyl and decaying radioisotopes we can't control. Energy is released when the light nuclei are fused because the fusion intermediate product does become a fission product, but it fissions generally into other light atoms that are not radioactive. The ultimate fuels are fusing hydrogen nuclei together, and that's what runs the sun. Other common elements, light elements, can do that, and they include lithium, boron, and helium isotopes. Some of the reactions are radiation-free, and others are not. I just want to show you the energy levels. We all know about chemistry, fire. Hydrogen and oxygen burning makes H2O, and it gives you about 10 units of energy measured in electron volts. If you take deuterium and tritium, the two heaviest isotopes of hydrogen, and cause them to make a helium-4 and a neutron, you get 17.6 million units of energy. That's why fusion energy is so exciting. It gives us remarkable bombs and other exciting things. Fission, on the left, there are 3 stages. If you have a heavy, unstable, nearly unstable nucleus and add a neutron to it, it will start that nucleus oscillating. The energy, binding energy of the neutron will cause the nucleus to oscillate, and eventually it will break into 2 parts and give more neutrons than it occurred at the beginning. And one of these neutrons goes around and can start the chain again. That's the fission chain reaction, giving you 2 radioactive isotopes. And that, of course, is what gives us Hiroshima and Nagasaki and all the excitement of the world. Fusion is a different thing. This is the deuterium-tritium reaction giving you the helium-4 and the neutron. The others are similar. The one we're most interested in is this one, because it's very odd. It's a boron-11, which has a charge of 5 in the nucleus, and a proton, a hydrogen nucleus. If you add the two together, the binding energy makes an excited state carbon-12. Carbon-12 is one of the most stable nuclei in the universe, but when it's excited by the binding energy of the fusion process, it's unstable and it decays to a beryllium-8 and a helium-4. The beryllium-8 very shortly, 10 to the minus 13 seconds later, decays into 2 more helium-4s. So this process is unique. It's the only nuclear energy releasing process in the whole world that releases fusion energy as 3 helium atoms and no neutrons, no radiation. It's radiation-free, which means if you build a machine that runs on that and you turn it off, you can go sit on it. There can be no 3 Mile Islands and no Chernobyls. It's difficult to do, but these are the favorite isotopes to use, protons, deuterons, and tritons. And as I mentioned, this gives us this nearly 20 million units of energy. The intrinsic energy gain from DT, which is what the world is chasing, is about 2,000 to 1. But of course, the means that the world are following won't work that way. The neutron-free reaction here gives us 8.7 million units of energy, and we can reburn the helium-3 deuterons when they fuse, split into 2 channels, a triton, which is radioactive, and a hydrogen nucleus, and a helium-3 and a neutron. That helium-3 can be cycled back through the exhaust system you have to have on the system and reburned with another deuteron to make more energy, so you get about 10.2 million units of energy. The D plus T gives you this ridiculous result where most of the energy is carried by a 14 MeV neutron. And the reason people look at D plus T, and I apologize for this graph, but this is a cross-section. A cross-section is a measure of the probability of a fusion reaction happening when you try to bring 2 particles of similar charge together as a function of the energy of the particles. The higher you make the energy, the easier it is for the particles to overcome the Coulomb repulsion between the 2 charges, and the closer you get them. You have to get them within about 1.3 Fermis of a distance before the nuclear forces will grab them and make fusion. And D plus T has a probability curve like this. It goes way up here at an energy of about 40 kilovolts. The PB11 system, unfortunately, in this particular target frame, peaks at around 560 kilovolts, very much higher, very much harder to do, and impossible to do in any system that has a Maxwellian distribution of particles, where all the particles are mixed and they're all in thermodynamic equilibrium. Because most of the particles that make fusion are not at that energy. That's the tail of the Maxwellian distribution. And most of the particles in a Maxwellian system are at much lower energy, incapable of making fusion, but very capable of making what's called Bremsstrahlung radiation from electrons oscillating around ions in the system. The original physics, the physicists in the original program back in the middle 1950s remembered their high school physics very well. And they said, how are we going to contain neutral plasmas in thermodynamic equilibrium? And they remembered the right-hand rule. You know, if you have a current flowing this way and a charged particle going this way, the force on the particle is at right angles to those two. The force in a magnetic field is not a restoring force. It doesn't restore the particle from the direction it's going. It's always at right angles, the right-hand rule. So they said, you can't contain particles without a field because they'll run straight into the walls. So we'll put a magnetic field together and all the particles will gyrate on them. And this is going to trap them. So all manner of configurations were devised to trap them with magnetic coils that tried to bottle up the ends where the particles would all go out, and solenoidal magnets and cusp magnets and reflection and mirror magnets at the corners. Cusp, this is what Livermore spent $2 billion on. It's an impossible system because it has a point cusp, North Pole, South Pole, and South Pole is the equator, and the losses out these equatorial line cusps kill you. And so the physicist, of which I was one, said, let's close up the solenoid and make it closed so the magnetic fields never end. And now the particles will stay here and circulate round and round. But there's a physics reason why you can't just do that. You have to have a poloidal current and a circumferential current. So they invented the tokamak. Lavrentiev in the Soviet Union invented it. I often thought he invented it and gave it to us to make sure we never got there. And that's what we have now. And the tokamak, let me explain something. That's the ITER tokamak, 30 meters across, 110 feet tall. That's a normal PWR. This is about the size of the machines we hope to build. And the reason that these machines, these mixed magnetic confinement machines, which don't confine in local thermodynamic equilibrium, are so big is very simple. It's that picture I showed you of the magnetic field in a tube. All the particles gyrate, and they stay there very happily, so long as they never collide with each other. The moment two of them collide, the guiding center for that collision jumps 2 gyroradii. So every collision causes those particles to jump towards the wall. It's a random walk process, but it turns out it takes more than 1,000 collisions, scattering collisions in DT before you get a fusion reaction. That means you have 1,000 gyrocenter jumpings to go through before you have a probability of a fusion reaction. It's a random walk process, so the distance is the square root of 1,000 times the twice gyroradii. And that makes these machines have dimensions across the plasma regions that are measured in 2, 3, 4, 5 meters. You can't beat physics. The physics says it has to be that big. Furthermore, the DT reaction makes this 14 MeV neutron. The 14 MeV neutron is very, very energetic, and it has to be disposed of, and you have to find some way to create the tritium that you're burning, because it's not a natural isotope. It's a 12-year half-life beta decay. And you create it by capturing the neutron in a blanket out here of molten lithium. The neutron is captured in the lithium-6, which then makes tritium. It's what we use for the bombs, and the lithium-6. And you have hundreds of tons of molten lithium sitting around this giant plasma container. And outside that, you have the superconducting magnets that you have to have the high fields. And this whole thing is an enormously expensive proposition, which even some of its proponents say they don't think it might ever be economic, but it's really good science. No. The problem that we saw was that everything that they're doing is highly radioactive. It's expensive. It's measured in tens of billions of dollars. The projected run-out cost of ITER is $12 billion. The program over the next 25 or 30 years is another $30 billion. The United States has already spent $18 billion chasing this tokamak dragon. And the inertial electrostatic stuff comes in at the order of tens to hundreds of millions. There's no end in sight that we see in the tokamak world. Giant machines and no predictability. It's all empirical. One of my friends, Dr. Nicholas Kroll, a consultant to us, probably one of the top 3 theorists in the world, said some years ago he spent $15 billion studying tokamaks, and what we know about them is they're no damn good. But fusion works. All you have to do is go outside in the daytime or go outside at night and look up. There are billions of fusion reactors. Every star is a fusion reactor, every single one of them. And not one of them is toroidal. And they're all held together by a funny force that's not a right-hand rule force. It's a central force field derivable from the central potential. It always points to the center. No matter what the particle motion is, it's always pulling it to the center. So the sun and the stars run on fusion of hydrogen. 4 hydrogens together make a helium atom after you have some inverse beta decay going on. And the only other force we know that's like that is charge directed or mass directed, M1, M2 over R squared, or E1, E2 over ER squared. There's the electric field force, on charged particles, the Coulomb force. Charged particles of opposite sign attract, and direct forces and charged particles of like sign repel. So what we have to do is find a way to take electric fields, next slide. That's all right. Electric fields, and make them accelerate the particles you want to collide toward each other. How can you do that? You can't do that with any assurance if you just take a plain parallel electrode and do it. But other people a long time ago said you can do it in a sphere. You can make a spherical electric field. You can make these particles come to a focus toward the center. With a 1 over r squared convergence, fusion power goes as the square of the density of the particles times the cross-section, times the velocity of the particles, times the volume over which that acts. N squared sigma v volume. Density in these machines, because it converges as 1 over r squared, goes like 1 over r squared. Density squared goes like 1 over r to the 4th. This means if you can get a spherical convergence going, almost all the fusion will take place in little bitty region in the center called the core. And we were not the first to understand that. In 1924, Irving Langmuir and Catherine Blodgett, working in the East Coast, wrote a paper on currents limited by space charge, differences in concentric flows and spheres. In 1959, Elmore, Tuck, and Watson at Los Alamos published a classic paper on inertial electrostatic confinement of a plasma. And what they talked about was putting a screen grid, a spherical grid, like two sieves back to back inside a sphere, and biasing that sieve to a positive potential so that electrons from out here would be attracted through the screen, would go inside, and would make a negative potential well because the electrons would slow down. Their kinetic energy would be transformed into potential energy of a potential well, and you could then drop ions into it at the edge. The ions would fall down and recirculate back and forth, like marbles in a well. And if they collided and didn't make a fusion, they didn't get lost like a tokamak. They would go right back up the well and give their energy back to the well. So you could make a fusion machine that way. The only trouble with this is they had a grid. And you have to have, in the case of electrons, about 100,000 transits of electrons before you will get a fusion out of the ion population you will put in. And no grid is that transparent. The best grids that Hertz and Farnsworth could ever build were about 95 or 90% transparent. And if you have a high interception rate on the grid, all the energy you put into the electron acceleration goes into the grid. And the energy is lost and the grid melts. It doesn't work. You can't get there with grids. Hirsch and Farnsworth, Philo Farnsworth, who invented raster scan television, and Bob Hirsch, who was a postdoc student, worked for Farnsworth. Fort Wayne, Indiana, in 1967, wrote a classic paper here where they actually built a machine that inverted the Elmore-Tuck-Watson potential. They had a grid that was biased negatively, so they accelerated the ions directly, and that way they could get by the electron interception problem and replace it with the problem of ion interception, because the ions had to go through several thousand times and they could never get a recirc factor bigger than about 7 to 10. But this little machine that they built, which Hertz still has on his desk in Alexandria, Virginia, actually ran at 10 to the 10th fusions per second on DT, which was then and now is still a world record for such a device for that particular machine. But he did it with ion guns that were facing each other. So in a way, he had two guns that were spherically focused in a very carefully designed machine that Farnsworth designed. He was a brilliant designer, and tested it. The total gain of the system was about 10 to the minus 6, meaning the power output versus the power in. And that was because of the grid loss problem and the other secondary problems of collisionality of the walls. There are therefore two ways to do this. One we call ion acceleration and electron. Ion acceleration is what Hirsch-Farnsworth did, and there's the grid that kills them. And this is the Elmore-Tuck-Watson concept with the grids removed. What we did, the invention we made was very simple. It's elementary when you look at it. Just throw the grids away. Replace them with a magnetic field. Magnetic fields do not contain neutral plasmas worth a darn, and that's the tokamak problem. But they will contain electrons by themselves very easily because electrons don't weigh anything. A deuteron atom is 3,600 times heavier than an electron. So it's easy to contain electrons in magnetic fields, or there wouldn't be Avarian associates up here building high-power tubes. The point is, if you do that, you have no grid collisions. You replace that problem with the problem of how fast do electrons transport themselves across the magnetic fields to hit the walls of the magnets, which now become the magnetized grids. And you have a system which fundamentally you should keep open so that there can be recirculation. And what you do is you produce the Elmore-Tuck-Watson negative potential well, and then you drop ions into it at the edge. The ions see that well and they recirculate. I've showed here a central virtual anode because if you put a lot of ions in, it will push the anode up in the center as the ions collide. These devices are almost neutral. The departure from neutrality required to make a 100 kilovolt well is only 1 part in a million when you're at a density of 10 to the 12th per cubic centimeter. It's so small that we found that the current computer codes and computers available to us to analyze the problem were incapable of analyzing it because of numerical noise in the particle and cell calculations by a factor of about 1,000. The basic problem this kind of fusion. We have this is to make a quasi-spherical field. We can't tolerate this mirror loss with the equator that Livermore spent the time and money on, or other people, not just Livermore. We have to have a magnetic field that has only point cusps. Think about that. If you put two coils together and you make a North Pole, and have an equator, you have this huge loss equator line cusp. There's no way around that unless the topology or the configuration is correct. There's only one configuration that works, and that's the one we patented. It's a configuration which is a polyhedron where the coils are all on the edges of the polyhedron, and the polyhedron has to have the property that there are an even number of faces around every vertex, so that alternate faces are north, south, north, south, north, south. If you look at the cube, which constitutes the normal biconic cusp, it only has 3 faces around every vertex, and you have that line cusp problem. And that's the only thing we could find to solve it. And that's the solution, was to make a system that's quasi-spherical. There's no magnetic monopole, so you have to do it from the surface. So it's a bunch of cusps sticking out like that. And there are no line cusps, so you have only point cusp losses. And we trap energetic electrons in that and form the negative potential well and drop the ions in. And they're focused at this 1/r², and they oscillate across the core, as I mentioned. It acts like a spherical colliding beam machine. And the fuel gas input at the potential well edge is just nothing more than putting in neutral atoms and letting the incoming injected electrons ionize them at the edge. The ionization of the fuel, the neutrals, gives you a low-energy electron and a low-energy ion. The ions fall into the well. The low-energy electrons are heated by the incoming fast electrons very rapidly, microsecond timescales, and become part of the circulating system. Go ahead. I just showed this really quickly. Oops. There we go. This you've seen. The only thing I wanted to show you was this Maxwellian distribution problem. This is a local thermodynamic equilibrium, Maxwellian magnetic system. Here's the density distribution in a Maxwellian. Most of the energy is right here. You're sitting in a room where the temperature is, 78 or something, and all the particles are about 78. But way out here, 4 or 5 times out, are a lot of particles in the room that are much higher temperature than that. You don't feel them because there are not very many. And if you're in a system that has this potential well, that we're describing, all the particles at the bottom are at one energy. If you have a 100 kilovolt well and you drop in an ion at the bottom, they're all 100 kilovolts. They're not spread about. And the problem is in that these mixed systems, the fusion reaction cross-section, which goes up with energy like that, only causes these little guys to make fusion. And all the rest of the particles are losses. And what that has too going for it is, in the case, I'm sorry to do more details like this, but this is cross-section versus energy. You may remember the PB11 peaked at 560 kilovolts. Not if you drop a Z equals 5 boron into a 100 kilovolt well. At the bottom of the well, it has 500 kilovolts because it has a charge of 5 falling down the well. So I don't have to put 560 kilovolts into a system to make that one work. The ion fusion power, just 2 points. By doing it this way, we actually decouple the 2 problems. The big loss problem is the electron losses to drive the well. The generation of fusion power has almost nothing to do with that. However many ions I drop into the system, that's what makes the fusion. But I don't have a well unless I take care of the electrons. But the problem is to understand how the electron drive power is lost or controlled, and see how many ions we can put in to still make fusion. It turns out that we've done studies in particle and cell codes and movies and all kinds of interesting computer things that if you have no ions at all and you inject electrons, you'll make a deep well. It will be very sharp at the edge and flat in the middle. Then you start injecting ions and the well will begin to smooth out because the ions will go in. You inject more and more ions. You will finally get a well that is basically curved and very flat at the center, but you won't have enough density to make fusion. You need to put more ions in than that so that at the center, it's quasi-neutral, but it's slightly ion-rich. And then you begin to develop a little central virtual anode. If you put still more ions in with a fixed electron current, the virtual anode gets higher and higher and higher until it finally blows the well out. And the range between flatness and blowout is about 5 or 8 to 1. So it's not a control problem in the sense that it's millionths of a control thing. You have factors of 5 or 8 to play with in ion flow control. The magnetic confinement of electrons is critical to ensure that we have what's called cusp scaling. I've told you about point cusps. Point cusps are the things that people saw in what are called mirror machines. I showed you a picture where the particles came in and mirrored and reflected. The reflection coefficient in a mirror machine, a low-density machine like that, varies as 1 over the strength of the B field. That's not good enough. If you can somehow put so many electrons in there that you make the pressure balance equal between electron kinetic pressure and magnetic field pressure at the outside. B squared over 8 pi is the magnetic pressure, and NE is the kinetic pressure. If you can make those two things equal, you can't make the kinetic pressure greater because it will blow through the field. It's like blowing up a balloon too much. If you can make them equal, then you can push the magnetic field out. As you push the magnetic field out, the scaling ceases to be a mirror scaling and becomes what's called cusp confinement scaling. And it scales as 1 over the square of the magnetic field. And if we can do that, what it amounts to is we're making the loss holes through which the electrons go out smaller and smaller and smaller the harder we drive it with the electron injection, up to the point where we inject too many electrons and it begins to open up the cusp holes. And those equations are all understood now. And the question was, can we do that? We called it the wiffle ball effect because, as you know, the child's toy, the little plastic toy with the holes in it, if you put a marble inside it and shook it like that, sooner or later the marble inside would fall out a hole. It would find a hole. The smaller you make the holes, the longer it takes the marble to get out. That's exactly what we're trying to do. The other problem in electron confinement is magnetic insulation of the walls, all the structures that are out there, the containers for the coils, the things that hold the coils together, the metal parts. We have to keep them from being able to be seen directly by electrons without magnetic insulation. And that's turned out to be the devil in the details, which we finally resolved a year ago. The key issues are these two things. Could we make wiffle ball scaling work? And could we understand the mag grid transporter? We have done both of those in the last 12 years. The approach is low-tech engineering compared to the monstrosities of the huge machines. I once used to call them superconducting cathedrals. They're very much like the Middle Ages. But it turns out that curious, simple concept, quasi-spherical fields and all that, has enormously complicated and wonderfully exciting physics in it, all through it. Why? Because it's non-local thermodynamic equilibrium. It's a completely dynamic system with opposing counterflows of two different charges. The density change from the outside to the inside can be 10 to the 4th or 10 to the 5th, and there's a time dependence when you start it up. It's an unbelievably complicated problem, made more complicated by the fact that every charged particle interacts with every other charged particle. It's not like the neutrons in a fission chain, which only see you when you get within the range of nuclear forces. Every charged particle, because of Maxwell, interacts with them all. And a computer calculation to do this once was estimated by Bruce Copeland to do one all-up, start-to-finish, time-dependent calculation in one of these machines would take 1,000 hours on a Cray. And this is not useful. The R&D device to build is small and fixed and quick and cheap. Quick and cheap, not compared to my budget, but quick and cheap compared to what the $18 billion we've spent. And it's straightforward testing of critical physics. These are all classical physics machines. And that's one of our problems in trying to find people to hire. Nobody's trained in gaseous electronics anymore. Nobody's trained in gyrotrons and thyrotrons. And you can't find people who do the work of Langmuir in the 20s and 30s, and that's what we need. We drew a picture. This is very old. This is 15 years old, of what such a thing might look like. It's got the wrong kind of coils. We should never make box coils like that. We now know. But this is a truncated cube. It's a cube with the corners cut off. And there are coils here, and they all go in the right direction. It just gives you a general idea of the thing. And of course, being a good physicist, what you do today is you patent it. So we filed patents in 85, and they're issued in 89, and another one in 92, which we can pass over that one. But. And having filed a patent on it, because nobody seems to have patented this configuration, which we saw was the only one that would work to get rid of the grids. We said, let's see if we can't get a program to see if this is a good idea and will work. Well, the idea was to get a program that could produce practical nuclear fusion in a reasonable size which would yield useful energy without radiation hazards. That seemed like a perfectly sensible goal that we should have pursued, but it didn't fit the model of the main programs simply because it's too cheap, too quick. I show this chart only because it's one of the real practical engineering issues. There's physics in it, but it's really an engineering problem. Arc breakdown. In practical experiments, what kills us is arcing. Arcing occurs no matter what. This is a Paschen curve for plane parallel electrodes for hydrogen. The point of this curve is not that I choose any particular number on it. The breakdown voltage is that we have to be very careful in the pressure and the distance we have in the test setups. Never mind the machine, it's the test setups that kill us. If the product of the two is too big, arc breakdown occurs at hundreds of volts. We're trying to run these things at 10 and 20,000 kilovolts, or 10 and 20,000 volts. And of course, for plane parallel electrodes, it's one thing. If you have sharp points and corners and bolts and one thing and another, the breakdown occurs more easily. This is an engineering problem, not a physics problem.
We're on to the next.
Oh, good. Now I want to show you some pictures of some of the devices we built. I might just say, we started, no, there's a slide first, I'm sorry. There's a view graph. Yeah. Now, can we go off that? Yeah. Here we are. That was the second thing. The first thing we built was a small open polyhedral coil that we ran at a few hundred volts just to show that the scaling would work. And we did that. We took the program not to the DOE, because I came from the DOE AEC, and I knew that was hopeless. No, it's not a pejorative comment. It's the program at the DOE which we had created was this monstrous money machine that still goes today. And people tend to protect their rice bowls, and that's how human nature is. And I knew they would never want anything that would threaten those rice bowls. And in fact, I went to Bob Hirsch, who worked with Farnsworth, who was then research director at ARCO, and I asked him, Bobby, I said, what do you think we should do? He said, do not go to the AEC, do not go to ERTA DOE, because they'll never support it and they'll kill it. Take it to the DOD. So we did. We took it to the Strategic Defense Office, where Jim Ianson, who was an astrophysicist, was the technical director. He understood it immediately like that. He said, it's a great idea, we'll fund it. And he funded it through the Defense Nuclear Agency. And then later on, it was funded through DARPA. This was an early DARPA program in 1989, where we built a machine that was 190 centimeters across. It had coils like that picture that I showed you. Wrong design in retrospect. It had all these big metal faces out here that were not magnetically insulated, and we didn't know enough not to do that. In fact, the paper we wrote on the experiments here and published in '94 erroneously tells you that the electrons got lost in the guns coming into the machine. They did not. They got lost after they got into the machine when they hit these metal walls that were not magnetically insulated. You can say, well, it's trivially obvious to even those of meanest intelligence to see that would happen, but it wasn't to us. And that was the DARPA program. After that, we tended to abandon that closed box configuration, and we set out and tried a little bitty machine, 5-centimeter radius, and this was made of solid state magnets, so it did not have the complete magnetic field. It had line cusps around here. You can see the electron burns where the particles that come out and run into the machine. We did that just to test the idea of the polyhedral configuration. And the next slide, I guess. Yeah, that was the second one we built. This was called WB2. WB2 was 10 centimeters in radius, and look at it. It's a beautiful machine, but it's not sealed. These are all air core magnets, and they're uncooled because there's no way to cool anything at this size and scale. And so we had all the problem of outgassing from the insulation on the coils that crumbed up the vacuum system. And all the coils are touching. That's how you held it together. You welded them right there. Bad mistake in retrospect, but that's what we did. And we ran it, and the next picture shows you one of the... That's what happened when we ran it in 1994, September, October 94. We actually achieved a wiffle ball. This was the whole point. We achieved a beta equal 1 condition, but at very low energy because the drive systems were very low energy. And when we cascaded in the middle, it brought the energy way down, but it was a wiffle ball. We ran all these tests on air because Maxwell doesn't care if it's fusion or air or whatever it is, air or argon. And here you can see the high density in the core, and you can see the particles coming out through the cusps, and they returned around through other cusps. This was done in September 1994. the first test like this, and we thought, my God, what's happened? We've got an arc we don't want. A month later, in October 13th, we ran it again and finally realized we'd produced a wiffle ball machine. And that was a great and wonderful thing. It took us a month to understand what we were doing. And meanwhile, I gave a talk at a meeting in Pittsburgh by the Navy, Westinghouse, and the American Nuclear Society on advanced technology for the 21st century on this program before we had really understood we had the wiffle ball. And the talk was apparently successful because the ANS wanted us to give it as a talk at their annual meeting in Washington in May. And I turned to our contract monitor and said, what should we do? Should we accept this invitation? He said, no. Now that you've got this thing working, no more talks. Don't go to any more physics conferences. Don't write any papers. Just lay quiet. Just do your work and don't publish. So for 11 years, we had an embargo on publishing. And that's why it's difficult to talk about it, because there's so much stuff. We have hundreds of technical documents. The next slide. That was WB3, which was the larger version of WB2, and it was built only by budget limitations. We didn't really have any way to do anything bigger. We were running out of money. And this is another machine which has flat coils, square coil containers. You ever see a magnetic field that makes squares? No. All of them are curved. And so these coils inherently had huge areas of metal where the magnetic fields produced by the coils themselves would run into the metal. As soon as an electron gets on that field line, it's lost. Oh, I guess the next one. That was WB4, the next one we built. And it, too, was connected at the corners, and it, too, had square coil boxes. In retrospect, not good, and these we call dog houses that connected them because this was a cooled machine. It had square copper tubing with water cooling. Inside at 200 psi, we could get to 3 kilogauss with this and run at steady state, because eventually we want all the machines to run steady state. But this suffered from the same basic flaw, that it had square box coils and field lines that ran into metal and dog houses and welds at the corners where you could not avoid having the lines run into the metal. Next slide. That was WB4 put into the test tank. We had a Faraday cage put around it. These are some of our people who were working on it. We had to insulate all the supports because everything that was at the wrong potential would attract electrons and would ruin the power balance and the things we were trying to measure. Next slide. That was it running at one point, and I showed this because we tried every conceivable potential configuration to get this thing to go to high beta. We could not succeed with the power supplies we had in the lab. We only had about 100 kilowatts. And it turned out we knew we needed a lot more. We didn't have the time, money, and SDG&E didn't have the power supply. So we ran it. We tried putting this thing at a very high positive potential, and everything else at ground, including the emitters. The emitters came in from the side over there. And what happened was we trapped electrons, and you can see they beautifully came out the corners, just like that WB2 picture. And 95% of the current went straight to the coils, to the walls, and to the cage. 95% saw the walls and the cage as an attractor for electrons. It went back to their original birth. It would not work. We can't do it that way. Next slide. We tried also ECR. We wanted to ionize neutrals, find a way to control neutral ionization. Because if you can't keep the neutral population down, it will flood the core and make the well go away. And so we tried what's called electron cyclotron resonance oscillation. You put microwaves at 2.45 gigahertz into this thing, and every time, if there's an 860 or something like that Gauss line surface, at that line that resonates EB over MC, it resonates with the microwaves, and you can ionize the neutrals very quickly in that situation. And we did this. This was ionizing inside the machine. The next slide shows us testing out and ionizing it outside. We proved that we could indeed ionize using magnetron radiation from a microwave oven, a $99 Sony oven. We took the tube and the power supplies out and full-way rectified the power supplies and drove it that way. And that was fine. The problem with it is that in later tests we found that, well, I'll show you the machine in which it did, and I'll talk about it. Next slide. Oh, that was the lady who's the president of the company. She's smiling because we wouldn't have a company if she hadn't been there. She took care of all the administrative garbage, if you'll pardon me for saying that. The leases and the insurance policies and the constant government audits from the DCAA. Not only do we have to live with the IRS like you guys do, we had to live with all the government auditors. And so we had a huge administrative load. We had 64,000 pages of paper in a 12-year program. 35% of the funds of the program went into administrative reporting and documentation stuff. It's not like private industry where you can control that. And she's happy because we have just run give me the next slide. We have just run WB4 for the last time, and we ran it finally, knowing we hadn't enough power. We ran it on a big capacitor bank with a 400 kilojoule storage. We ran it for a few milliseconds, a fraction of a millisecond pulse output. We finally got enough current into the thing to drive it properly. Even with all those welds and corners, it took several thousand amps to get it there, which was way too much. But we actually got fusion out of it, DD fusion at 10 kilovolts. And that was a historic moment. We did it 4 times the last week of December of 2003, which oddly enough, the first time it worked was December 17th, 2003, which happened to be the exact 100th anniversary of the Wright brothers' first flight at Kitty Hawk. And one of the people who worked for us was Lauren Wright Jameson, whose great uncles were Orville and Wilbur. Who knows? At any rate, on December 24th, Christmas Eve Day, we ran it for the last time. And we're very happy because it was the first time we'd ever had a really true high-powered polyhedral system that produced fusion. Next slide. And that led us, because of time and budget limits, to the next machine, the WB5. This was going to be a bigger machine. We thought we would try to beat the arcing problem by using superior magnetic insulation all over the machine, not like that first one, which had those big plates, and see if we couldn't raise the pressure at which the potential well would still survive. And we built this with closed corners, even though we knew that you really had to have a recirculating machine. And we built it to WB5. You can see this thing. And here are all these coils, but still at the corners and at the seams, there are places that are not proper. The next slide. I'll come back to this machine. In the end, we learned that that wasn't the way to go, and I'll show you in a little while why. And so we built the machine finally in great haste. We were running out of money. Our budget had stopped in fiscal 2006. We were saved by Admiral Cohen and ONR, who gave us an infusion to carry us through calendar 2005. And we were going to run out of money and have to start terminating staff and closing down our labs, which we would have had to do in April, but he gave us survival money. And we realized in about May that WB5 was never going to work for reasons I should have had at this point in the talk. And said we have to have a machine that has no metal surfaces available to the electrons, and it has to be recirculating. And all the coil containers have to be conformal to the shape of the magnetic fields they produce. So we very quickly designed and very quickly built this device, which has circular toroidal coils that have and are spaced at the corners. The key is the spacing. The original patent was based on the idea that you have coils of 0 dimension. Brilliant physics idea. But the minute you make a finite coil thickness and try to put them together, the current carriers that are on one side make coils and fields that intercept the other side. You can't have those coils touching because field lines will run into the metal the minute you have a finite-sized coil, which we all do. So we had to space the coils so that they did not touch, so there was a place for the magnetic fields to go out between the coils. And the spacing has to be a certain number of gyroradii. It's too much to go into, but we built this with this kind of thing, and the connectors, of course, are the only problem left. But they had some magnetic insulation, too, because we connected the coils we connected the conductors from coil to coil through those, so there was a local magnetic field around the spacer. And this we built very hastily in July and August of 2005, and we ran it in August and September and early October to get beta equal 1 data, and then we ran it in November. Could I have the next slide? That's the coil system. Go ahead, next one. And that's how it looked finally when it went in the tank, and then go ahead. And that was it in the tank. It was really a very lovely machine. I think is that the last one? Oh, no, I'll go skip from that was WB6. WB6 worked. It worked like a champ. It did everything we had imagined that we should have done in the beginning, and it proved that we had all missed the obvious. For 15 years, none of our consultants, none of our review panels, none of our opponents, none of us, none of me, none of my staff saw these obvious facts, and we finally saw them in 2005 and built that machine. And when we ran it at the 12 kilovolt drive and 10 kilovolt well depth, it produced a pulse of DD fusions at 10 kilovolts, which is very low energy. that was about 1 × 10⁹ fusions per second. That's 100,000 times or more higher than Hershey and Farnsworth ever achieved in any experiment they ever did. It's a world's record. It was only a short time, it was about 1/4 of a millisecond. Doesn't sound like much on my watch, but it's several thousand electron transit times in the system. So from the point of view of the electrons, it's steady state. They don't know any better. They live on a different time scale. They're moving at 10⁹ centimeters per second. So, next slide. And in the process of this program, I've skipped over this, but we built a very simple thing, several very simple things called MPG, magnetic polyhedral grid. We wanted to try to see if we couldn't get somewhere with the scaling business by using water-cooled copper tubing in a single-turn coil. We could only run this at 2,000 amps because of the cooling limits, or we'd turn the water into steam. We couldn't drive it any harder. But the trouble is, with only a single turn, the ampere turns in the coils were so small, we could only get about 70 to 100 Gauss out of these things. So the B fields were really small. But nevertheless, we were able to run this with a 30 kilovolt drive and a 27,000 volt deep well, and it made fusions, but the fusions were limited by the fact that we didn't have enough current and couldn't hold enough density with those low fields. We could only get a ball in the center about 4 to 5 centimeters going, and it was producing about 1 × 10⁵ fusions per second steady state. But it did prove the polyhedral principle again. The next one. And that's it in the tank. Go ahead. And the last odd thing we did was build a very strange device, which we call PZLX. It's a single-turn copper coil. It doesn't look like a turn at all. It's hewed out of a copper block, but it's polyhedral configuration inside this metal container to take care of the stresses. The coils come in and turn around and make the polyhedral coil. And we did that with a solid copper block, very thick, in order to try to put huge currents and get gigantic fields in this thing, because we were concerned that people were saying, well, these fields aren't stable. They're not equilibrium stable and dynamically, but they are. And that's what we did. We ran this pulse at 200,000 amps, pulse for 3 milliseconds, off capacitor bank. And what we did, we had a Paschen arcing. Paschen arcing would break it down to 300 volts. So we drive it with an external electron emitter, arc break down the stuff inside as we turn the magnetic field on sub-millisecond time scales from the capacitor bank, or as we turn the current on. Oh, that's the magnetic field. And then it would grab the ions. When the field got high enough that the ion gyro radius was smaller than the cavity size, it would capture the ions, and you do adiabatic compression of the ions. And we could compress these ions very heavily, up to 35 kilogauss, and we did this about 150 times over a period of a year, and the fields are stable as a rock. Why? Because MHD theory is correct. If you have a field that's convex toward the plasma at all points, it's always stable. It's only when it's concave toward the plasma that it's unstable. And all these polyhedral fields are convex toward the plasma. And we got neutrons and fusions out of this thing, and they agreed with the adiabatic snowplow codes and theories that we had that were perfectly correct. Is there any more? I don't think so. Oh, yeah, I guess that's the machine in the drive tank. You can just go through this quickly. That's that little one. This is the drive system we had. That's a capacitor bank back there. Here's the tank it was in. Go ahead. That's more of the same. This is just part of our lab, one of our guys. This is some power supplies. The electronics lab. Go ahead. And here was the a big gray vacuum tank we used for some testing. You just cycle through it, Michael. This is, where am I? This is the side of the main vacuum tank and the pumping system. No, this is not. Oh, let's see. I'm too close, I can't see this. This is a battery bank. We had 240 RV batteries to drive the coils. We could put out several thousand amps and controllable with IGBT controllers, so we could keep the voltage control. Go ahead. And this is, where are we? This is a power supply, neutron power. Go ahead. This is a water tank. We had to have deionized water and all that stuff and keep it cool because the coils would heat the water a lot. Go ahead. This is a 12-bank capacitor arrangement that stored 400 kilojoules at 15 kilovolts. And we had, Marx lines and things. These are some Hippotronics high-voltage power supplies that we used to drive the electron emitters, but they were limited to like 5 amps at 15 kilovolts and 2.5 amps at 30. Let's see, next one. This is the controller for all the vacuum pump or the turbomolecular pumps we had on the main vacuum tank. There's 6 of them. Go ahead. This is a control point. Go ahead. Next one. That is the gray tank again. We have too much. Just go ahead, Michael. This is a small vacuum tank in which we did the WB2 testing back in Manassas, Virginia, a long time before. Go ahead. That's more of the water system. That's the big tank. I'll see it again. That's the main tank. It was 2 meters by 3.5 meters. It would go down to 10 to the minus 9th torr. It was really a pretty good vacuum system. And it was hinged. You could open the door. That's the small gray tank. Go again. That's just more of the same with an L. The turbo pump was here. Next. CP again. Next. Oh, well, this is calculation. Skip through these, Michael. Go ahead. Okay. Yeah. Now, I wanted to show you something about WB5, that big box with the green coils that was not open and recirculating. This is the potential well as a function of the density of the starting neutral gas in the system that was used in that original DARPA program with the great big 190 centimeter black thing. We found that if the starting pressure was, the density was above somewhere between 1/10 and 1 times 10 to the 8th per cubic centimeter, and this was a pulse, we had to run this thing pulsed, 25 millisecond pulse, why the potential well, which was originally set up, would die right here. It would start to die. Why would it die? Because the pulse would create ions out of the neutrals, and the ions immediately would see the well that was forming, and the ions would rush in and flood the well and make a central virtual anode and blow the well out. Couldn't be stopped because we didn't have steady state control. Why didn't we have steady state control? Budget, money. It was a DARPA program, $50 million, and the director changed 4 months after it started, said we don't do fusion in DARPA. So he killed all the out-year money. So we could never actually build what we started out to build. But this is what happened. It died at this density. The next chart shows us what happened when we built WB5. Here's the DARPA thing here as a function of pressure. And here's what happened in WB5. We actually managed to move the pressure, the starting pressure at which it died, up a factor of 1,000. We said, oh boy, we're winning. We're going to get there. Where do we need to go? We need to go to a pressure approximately 100 times higher to get to densities of ions high enough to make useful fusions in the middle when they coalesce. We were 100 times too low. We were not 10 to the 8th or 10 to the 5th times too low. So all we needed to do, we said, was put 100 times more current in it. Hot dog, we've got that capacitor bank. We can put 100 times more current in it for a short while. So we did. But we'd done some electrostatic code calculations to show us magnetic or electrostatic potential lines, and the next one is even more compelling. This shows us where the electrons went. And lo and behold, where do they go? They went to the corners, to the seams where there wasn't any magnetic field. Sure enough, the magnetic fields produced by the coils insulated the surfaces beautifully. That's where we got that factor of 1,000. But as the fields turned around and came out through the corner, they went straight into the walls. And that's a railroad track for the electrons to get lost. And so we put 100 times more current in, and we gained a factor of 2 in pressure. And we said, this is obvious. This is the obvious point that we all missed. It's trivial. Of course, you can't have anything that does that. You have to have a machine that doesn't do that. So that's what caused us to build, no, don't do that one, build WB6, where we didn't, Oh, good. Okay, that's okay. Caused us to build WB6, which had conformal coils and spacing and had no magnetic fields running into the middle. And sure enough, that's what we got. We got neutrons out of here, and then the counts are 3 because it's a pulse system. When neutron counters are sitting several meters away from the device, we had 2 sets of neutron counters. And the neutron counters count 1 click at a time, and it's 4 pi radiation. So if you have a pulse, you got a lot of area to cover. We only had such a big box for the neutron. And we got 3 counts, and that turns out to be about 4 times 10 to the, if I could read it, I'd tell you whatever it is. When it came out over the pulse width, because the pulse width was only about 1/4 of a millisecond, it came out to be 10 to the 9th fusions per second. We didn't know that. I'll just tell you a little history in WB6. When we built it very hastily. We built it as quickly and cheaply as we could, considering that it was toroidal and it's hard to build. It's hard to build circular coils in a lab where you're winding them yourself. You don't have any money, and you're running out of time and money. We had to close the lab down on the 1st of November. It was already November 2nd or 3rd when we finally started to do these tests. We had to close it by year-end calendar 2005 because budget was gone. And we were running these tests on the 9th and 10th of November. The problem was that we had run the machine quite a lot before at lower voltages and higher densities to study beta equal 1 conditions, when we could get to beta equal 1 by running it on a high current, low voltage power supply. We'd run it probably 50 or 100 times to get data for the transport equations. So all that time, every time you turn a coil on, the magnetic forces in the wires tend to push them apart, move them. And they had been moved a lot in all those tests. So we ran it on the 9th and the 10th of November 4 times, and 4 times we got these results with fusion neutrons. And on the 11th of November, we tried to run it once again, and the coils had moved. This is much higher voltage and drive. The coils had moved sufficiently. They were just coils that were covered with normal varnish type insulation. And they had somehow worn through at one corner, and it shorted at the feed through, and the battery bank discharged through the coils and blew the machine apart. That was the 11th of November, and that was already 11 days past the shutdown time for the lab. And the following Monday, it was a Friday, the following Monday we started to tear the lab down. Nobody had time to reduce the data. We just had the data stored on the computer. And it wasn't until early December that we reduced the data and looked at it, and we said, oh my God, look what we've got. We've got something that beat Hershey and Farnsworth by 100,000. It works. We didn't know that for a month. It was like WB2 and the wiffle ball. And once we knew that, that was, what do you do? Nobody seemed to care. So we closed the lab down and put all the equipment together. And the lady you saw, who was the president of the company, said, why don't we save the equipment? Well, we can't save it. We have $1 million worth of Navy equipment sitting there, all that lab and all that stuff. She said, why don't you find a company locally that can take this equipment and we can transfer it to it as a DOD contractor? And I happen to know a man who was running a company like that, not 10 minutes away from us, a man called Jim Benson. Maybe you know him. He runs a company called Space Dev. Space Dev built the engines for Spaceship One that's hanging in your lunchroom here. They're a rocket company. Jim Benson, I've known for 30 years. Very bright guy, and he's absolutely intent upon making this happen for spaceflight. My original goal, too, because it makes space engines of incredible capabilities if it works. And so I got together with Jim Benson at Ms. Gray's behest, and we transferred $1 million worth of Navy equipment to him. All that vacuum stuff and all the pumps and all the power supplies in the labs. And he hired our 3 best lab people. So the lab still exists, just that we don't have it. He has it. I don't care. Let him do it. He's got a bunch of good guys. And he would like to pursue that program. Next slide. Oh, no, this is, oh, yeah, one of the things on the outline said, I'll tell you all the things we've learned. I won't tell you all the things we've learned. It's too much. It's 11 years. But there's a paper that I submitted, and it will be published from an international conference in Spain early in October, International Astronautical Congress, 1,500 people, 150 nations. And I put this paper into the Congress because I wanted to, for the first time in 11 years, put a summary out in print that says what we did and what we've learned and what it's about. So there is a paper available, if anybody wants it, that describes it all. It's not a very good physics paper because it doesn't contain all the equations, it doesn't contain all the theory and the models, but it talks about it all. And it gives a lot of references. And I think you can probably get that somewhere. I don't know where. But it's out, point is, it's out in public for the first time in 11 years. Yeah. I guess no. Isn't there one about codes?
We skipped codes. Way out.
There were? Oh, okay. Well, I can't help it. Let's see. We have codes. I'll just say we have codes that show power balances in these things. And power balances, power and gain as functions of the size of the machine, of the voltage and the size of the machine. I'll just skip ahead. We have a lot of graphs we could show you, and Noel tells me we're out of time, so I'll just skip all that. But to assure you, we do have lots of codes, computer codes of various kinds for heat transfer magnet design, for potential and density distributions, and Vlasov equation modeling, and one thing and another. We've also looked at, for EPRI up here in Palo Alto some years ago, looked at machines that would make utilities feel happy, and we think this is the best one, the DT catalyzed by the helium-3. We call it Cat A. It makes a neutron. You capture it in a blanket to make more steam. It minimizes radiation hazard. It has the advantage that it makes processed steam. This is not PB11 clean. This is DD making things that look like PWR neutrons, but it makes PWR steam. So you could build a machine like that and put it in a blanket, put it in a container like that, and then take that particular container and put it in the central part of a power plant where you have a number of them lined up in a row, and then that's the reactor building. The rest of this plant is normal plant, steam generators, steam turbines and generators and cooling towers, and this is a way you can retrofit existing fossil fuel-fired plants. You come in, sit down next door, build a little reactor building and tie it into the existing steam lines, and don't trouble the guys with the oil tanks, leave them there. But now you can turn the oil tanks off and run the thing on the steam that comes from the DD fusion system. And it's no different than a PWR system in the sense of the neutrons it produces, except when you turn it off, there isn't any radioisotope product to decay and kill you. We did most of our work for the Navy. Whoops. Somehow. And what we found for the Navy, we can make power systems like that. In the long run, the Navy's interested in PB-11. The Navy wants to convert the whole fleet to electric ships. And this is a way to make an electric ship that is nuclear but has no radiation, unlike the submarines. And it's relatively simple engineering. Commercial viability is in like 6 to 10 years from the time we prove the first main demo plant. And the cost, as we estimated today, is 150 to 200 million. This was a chart from 1994. And the Navy system looks like that. It's actually, forget this is a homopolar motor driving a propeller, but the power plant is here. And it's 14-foot diameter PB-11 sphere, cryogeny, and inverters and capacitor banks. That fits in the power bay of a Arleigh Burke destroyer. And it would run as long as the electrical system's held up, as long as Westinghouse can make the standoffs for the 2 megavolt output. Now, I want to talk about why are we doing all this? Who cares? Are we doing it for fun or for the Navy, for the DOD? We're a one-contract company, sole source, proprietary, without any competing. We never compete for a contract. We've had sole source contracts from the beginning. We've only had one contract, which is, of course, why we died when the money failed. But if we can make it work, you can stop the greenhouse effect. You can make power plants with no off-gases, no atmospheric smog. You can stop acid rain, stop all thermal pollution. You can build a DT system that will burn up nuclear waste. We did a study of that in '93. Showed a DT burning system can make so many neutrons that you can burn up the nuclear waste from 20 power plants in steady state time and make power at the same time and sell it and change the storage time from 4,000 and 9,000 years down to 40 and 90 years, which is more tractable. So it's an inexhaustible source. Hydrogen is everywhere. Deuterium is everywhere. Deuterium is 1 part in 6,000 in every glass of water you drink. Small scale and low cost, and it's probably because I've said that. Electric fusion plants one of the interesting things they can do is make really cheap ethanol. We went to Vulcan, Cincinnati, an ethanol plant builder, and Ingalls Shipbuilding in Pascagoula, a division of Lytton, and asked them, what about putting an anhydrous ethanol plant on a barge run by these guys? And they said, yes, 50,000-ton barge can produce 6,000 tons a day of anhydrous ethanol if you put it in Brazil, and you run a 30-mile square cane field, which has 2 crops a year, and because you don't have to use the pith and the husk as bagasse for fuel, you can ferment the pith as well as the juice, and the husk you can take off with a Canadian process called the Tilby process and make wood products out of it and get some income from it. And you can get anhydrous ethanol at 25 to 30 cents a gallon net cost. And that's not bad, but the big oil companies might not like it unless you gave them a license to do it for themselves. And this means that all the third world countries in the tropical belt where you can get 2 crops a year can become oil producers. Very interesting. You can burn up nuclear waste, fresh water. You can certainly make practical space flight. In that 11 years, we were embargoed from writing papers. The Navy allowed us to write papers on what you could do with this if you had it. So we wrote a series of 8 papers on how you can make rocket propulsion and space flight practical if you had this thing. They're all in print. It brings global economic stability, and that's really the main driver. Cheap, clean power, make it readily available. Makes fixed energy prices. We don't have the OPEC up and down game. Low-value cane in third-world countries becomes a high-value export product, and all the third-world nations can become economically viable, provided you set up the business arrangements in the right way so that the people who are building the plants and making the alcohol are forced to pay some portion of the profits back to the third-world countries from which they are taking the cane. You can make a profitable industrialization possible in third-world countries because they will have money. And that's the whole name of the game. Destroys the world market for gasoline, eliminates the oil cartel, and while the oil states suffer income losses, what they really need is food. And how do you get food in many of those states? You need water to irrigate, to make agriculture. But these plants can make desalination plants so cheap that you can afford to make food. You can make desalination plants that run at 1/20th of the cost of what the Saudis now pay for desalinated water. And that allows you to do agriculture. And if you can do that, you ought to be able to stabilize the Middle East by economics. Never mind ideology. Money talks, you know. The oil wars should vanish and so on. The third world becomes fiscally responsible. Now,
It would be useful if we could ask questions for a while. I think we're all...
yeah, is this the last one? No, there's one more chart. May I do one more chart? Or is there two? No, there's two more. The end-use market price of all these energy products that this machine can replace, which will be a 40-year replacement time, is $5,000 billion a year, as estimated by the Chase Manhattan Bank in the 1990s, into year $2,000, $5 trillion a year. If you do this by building a machine, doing the R&D, and leasing everybody in the world to build these things. We don't want to build them. Lease everybody. GEC, UK, and Korea Electric, and Brown Boveri, lease them all over the world. Lease them and charge them a royalty fee of 2% of gross. What you will generate is $100 billion a year of profit. That's a business. It's the biggest business in the world. What we need next, we know the design scaling. It's a 4 to 5 year program. The design scaling, actually, I don't have a chart. I do have a chart, but don't bother with it. The design scaling we've learned is very odd on this machine. The power goes as the power output goes as the 7th power of the radius. 7th. As you make it bigger, the power output suddenly goes up. The gain goes as the 5th power of the radius. That means that there is no point in building something half size. It isn't going to get you anywhere. It's down by 2 to the 7th. So you might as well go the next step, build a full power demo. How big is it? 1.5 to 2 meters radius for DD, 2 to 2.5 for PB11. Doesn't get any bigger. Doesn't become aircraft carrier size. It's that size. We were always working at 1/8 to 1/10 of the size, but we could learn all the physics there. It took us a long time. It was very cheap. We had 5 to 10 people working for 12 years, but we learned all the little physics. Doubling the size won't give us any new physics, not until we get to the full power size. So that's the next logical step. And that step will cost about $200 million. I don't know where it is. There's a lot of engineering problems. The physics problems are gone. The engineering problems are the things we have to do. You have to get Minhoney or Raytheon or somebody to come in and do the instrumentation and control. We need to have somebody come in to do fuel gas control feed systems at sub-millisecond time scale. We have to do a lot of engineering things, which we know how to do. But engineering costs more than physics, factor of 10. The first year we want to do 2 more machines like WB6, have an enormously high-level review panel with the most senior people in the United States, all of whom are probably over 70, because they're the only ones who know enough to know what the hell we're talking about, and have a demo program plan, and in the second, third, and fourth years, develop and build a machine, and build and test the demo plan. We can do that in something like 5 years. Is that it? That's it. And that's what we're trying to do. We need $200 million. We don't need it. I'm not going to do it. I'll be an advisor. But Jim Benson and his company, maybe Google. This is the most exciting program I know in the world, or I wouldn't be working on it. I think that's why you guys are all here, because you have an exciting company and you're doing exciting new things. This is something that can change the world completely. It's like the shift from wood to coal, coal to oil to nuclear in France at any rate. And this is something that's even more profound than that because it affects every single energy program on the planet once it gets going. This is not an attempt to kill oil companies. It's an attempt to change the way people live and the way politics works and the way energy is available to humankind and the way nations that have nothing now can have something. And we thought that was a pretty good objective, and we still do. And I will tell you, the reason I began publishing after the embargo's gone, because they don't pay us anymore, is because I'm intent that this program shall be done. And if we can't do it in the United States of America, somewhere it'll be done. It'll be done in Hefei, northeast of Beijing, or it'll be done in India, or it'll be done in Brazil, or Argentina, or Spain, or Italy. It'll be done somewhere, or Venezuela. We can put enough cheap steam down in the Orinoco fields to get that oil out at a lot less than $30 a barrel, and they have 7 times their reserves of the Saudis. We may not like Chavez, but he's got a lot of oil. And we have a way to go. Somebody out there will do it if we don't. And I think it's a shame if we don't. I came here because who knows, your Google mentality says maybe you guys will do it. Thank you. Question? Question here. I'm sorry I took so long. You have we should have questions and answers if I can give any. I guess, yes.
There's a lot of theorists in this community in these microstructured and nanostructured metamaterials that have negative index of refraction for microwaves. I wonder if those expand the design options for electrostatic confinement.
The question is, if the metastatic materials which have strange indices of refraction, will that give us any hope in the magnetic confinement business? I don't think so, and the reason has nothing to do with their properties. I think that they're just in another world that we don't interact with. Everything we are doing is in enormously high magnetic fields, and it's an environment that's totally hostile. It's very high energy particles that are, in the case of PB11, up to 200 kilovolts, and huge surface damage from impacts. And so I don't see how the solid state machine, those solid state devices have any particular role to play in this machine. They might have some use in external control systems, but not in the device itself. And that may be a bad answer, but that's the only one I know. Yes. No? Oh, here, where?
If I were personally able to write a check to fund this, I would. But first, because the WB6 was destroyed, and there's no working prototype that actually would demonstrate that we understood the physics and the engineering, I'd ask you to rebuild WB6. What would that take?
That's the last chart. That's the first year of the 5-year program.
That wasn't the first time I missed that.
No, it wasn't clear. It's called WB7 and WB8, right here. The first year will be 2 small test machines, which are called WB7 and 8, that are like WB6, but not, because they're not circular coils, which are not optimum. They will be actually coils that follow the polyhedral configuration, but they will be carefully spaced, and we expect them to work 3 to 5 times better than WB6. One of them will be a truncated cube, and one of them will be a truncated dodecahedron. And those are 2 machines that we will do to do just exactly what you asked. We will do WB6 improved 50 times more so that we can hammer that data down so that the senior review panel will have something to look at.
Reduce the risk.
Yeah, it'll be there. And I wouldn't convene that senior review panel without having that data to say, look, here it is. Now what do you want to do? The first year, just to do that's $2 million. But if you're going to go on to the full program, which you should do, you might as well program it for 5 so you can get some run-up on the main program. You can't hire good people if you're in a 1-year program. But that's key, absolutely key. Yes?
Where is your paper available, and are you going to be publishing more?
I'm trying to get to writing a very long paper, about 120 pages with all the mathematics in it, not all, but some. I don't know what to do with it. We have this much paper. This paper, Noel said it's not available on the internet. It's in the proceedings of the International Astronautical Congress held in Valencia in early October. It's supposed to be on the internet, but he can't find it.
The proceedings aren't out yet.
I have it. I suppose you could write me and I'll send you a copy.
Digitize it.
Well, it's PDF on it's somewhere on the.
There's actually a copy in WIS or GFS.
Mm-hmm. Yes.
In steady state, how do you actually extract the helium nuclei from the core?
It's Noel said I should talk about that. When you do PB11, you get 3 helium nuclei. One of them's at a fixed energy of 3.46 MeV, and the other 2 are average 2.4 something. And they're average because the beryllium-8 that decays is moving, so they run between about 100 kilovolts and a couple of MeV. That helium, you have to take the energy out by having grids external to the machine, electrically biased grids. So the helium nuclei charge up against the grids, and when they run out of energy, they will hit that next grid. Okay, when they hit the grid, they become neutral because they're neutralized by the electron. And then you have to have an exhaust pumping system that pumps all the external gas out all the time anyway, because you can't afford to lose all your fuel. You can't afford to lose the boron and the hydrogen. So you have an exhaust system in which you then have to have separation processes to separate out the helium from the protons and from the boron. And we've done a study of that for Los Alamos. We have a whole paper on it, looking at centrifuges and electromagnetic separation, cryogeny, and one thing and another. And it's perfectly straightforward because these are all light elements where the mass differences are really quite sizable. And if they're not mass difference sizable, like T and helium-3, they cryogenically condense at different temperatures. So it's really straightforward to do that. You take the trash out that way. You take the energy of the helium fusion products out by grids. It's like a giant battery, a beta decay battery. Yeah.
So other than an engineering challenge, it looks like getting funding is the deal. Are there any other impediments?
Not that I know. I really don't. I mean, engineering is not, you just don't do that. You have to have really good people. Westinghouse and GE and Raytheon and a lot of good people come in to help you and to do all the engineering of that heavy stuff. You want to do 200 kilovolt standoffs? I don't do that. EPRI funded Westinghouse to do that. But we have 800 kilovolt and megavolt transmission lines running across the country, so people do know how to talk about those things anyway. The impediment has always been money. We've told the Navy and the DOD since 1989 that the cost of this program in today's dollars is $200 million. We've had it in report after report after report. And they knew that. And they knew that from the beginning. And they said, we can't do that. Why can't you do that? Because if we do that, I'll tell you the story. If you do that, it becomes visible to the staffers on Capitol Hill. It's a big enough budget item that people see it. Once it becomes visible to the Capitol Hill staffers, everybody on Capitol Hill knows that this is what the Navy is doing. The DOE will see it. The DOE will say, no, you can't do that. We have the charter to do fusion. And that's the end of the program, because they will co-opt it and shut the Navy down. So the Navy had to fund us at a low level below the radar screen of politics. And that's exactly what happened. And it's nature, it's life. And there we are. The funding has always been way too small. We had a staff between 5 and 10 people doing this whole thing for 12 years. Microwave ovens. I mean, we actually learned all the physics slowly, but we learned it all. And the engineering problems, of course, are way beyond those budgets. We couldn't even run the machine steady state. We had to go to these cap banks. Going to small size and cap banks makes the experiments very difficult because you don't have time, you can't build cooling, you can't control the gas flow. We had sub-millisecond pulse gas inputs, but we couldn't turn them off in time. It's very hard. It's much easier to build a big machine in the sense of the control problems. And we need, not we, I don't need it, but whoever does this needs a lot of help. The Chinese at Hefei could probably do it very straightforwardly. Question?
You said that a lot of the people or the old people who do this were trained in some of these areas are over 70 years old. That seems like a problem going forward. Or is anybody looking at,
Yeah. The question is that I made a sort of jocular remark that the review panel would probably be people over 70 years old. I don't know that that's true. I'd actually have some people in their 30s on it because I know some very bright guys. The problem is that engineering schools in nuclear engineering and in physics, related physics, really don't train people in this field anymore, and they haven't for 20 or 25 years because it's an arcane field that doesn't fit modern technology. We've all gone to silicon. We've all gone to microchips, and we've all gone to solid-state devices. And there are very few people who make giant 4-foot-high power tubes. It's not like the days of Langmuir and Tesla and those guys. This is really back in that world. It's not that anybody's evil, it's just that there wasn't any market for people like that. So the people who lived through it, I'll give you one example of one of the people I'd like on that review committee. His name is Bob Simons. He was head of research at Varian for years, and then he was head of lit and electron devices here in San Carlos. And he's been following this field and working in it for 35 years. He's 86 years old, but he's smart as a tack. I mean, he comes from another world, and there's nobody trained in the schools that you can turn to. I happen to know some good people at Sandia and Los Alamos, some really bright guys who I would turn to put on this panel, because they think outside the conventional magnetic confinement box, and that's the problem. The box has become so big and so well funded, it supports thousands of people in hundreds of labs all over the world. Everybody for decades has been thinking about Maxwellian equilibrium plasmas. And it's very hard to break that mindset. If you live in that box and your income comes from doing research in that box, how do you ever break out of it? Well, I know a few people who do. I know a man at Cullum who I would bring in as the director of research from England, because he's appalled at what he's doing. But he's working on JET, which has been being studied there for 24 years now. It's a very difficult problem, but it's a real problem. And I even discussed this with Bob Hirsch, who's still in Alexandria, as to where we would find people. And how do we find people who are credible? Well, I can find a lot of people over 65 who are really credible, who have been brilliant engineers in their lifetimes, and who have national and international stature, who I would trust. And I don't own these guys. They're just friends of mine. And we don't lie to each other. And they would tell me what they really think. And that's what I want. I want the brightest guys I know to be there to tell me what they really think. Should we go ahead, or should we say, no, it's too big a risk and why bother? I don't think that's going to be their answer. Yeah.
I wasn't entirely clear on your plan for funding. Were you trying to move towards like a private corporation or get government grants?
We've given up on the government in the sense that I find no one in the government who is at this point remotely interested in doing it, and anybody in the government you see is staffed largely by people who don't have a physics background. And the staffers, many of them don't really. And this is, as the chart said, it's very complex and arcane physics. And this is not a fault, it's just the way things are. The government, it will always turn to its government labs for an assessment. The government labs will say, no good, absolutely no good. I've been through that for so many years, it's beyond belief. These are my labs. I used to be an assistant director at Los Alamos. And in the AEC. And I know these guys. I mean, they're all my friends. But they're going to all say no, except for a handful of guys I know in those labs who think outside the box. And those are the good guys. I'd put some of those young guys on the panel. Yes?
This may sound a little bit ludicrous, given that a lot of this was developed through experimentation. But what about the possibilities of being able to use computer simulations to advance some of the state-of-the-art here?
Yeah, I passed over that much too quickly. We have been doing computer simulations of these since 1989, starting with Bruce Goplin at Mission Research with the MAGIC code, which is a particle and cell code from which we could make beautiful movies of these little particles moving in and out, and going through numerics in Albuquerque with Jack Watrous, who used to work on the program. And it's numerics as a subcontractor doing more particle and cell calculations that halfway through their contract, they said, we give up. We can't calculate this problem. The problem is, how do you do a calculation of the magnetic field being expanded toward the beta equal 1 condition, the pressure balance condition, in a transient way with all this Maxwellian interconnection, and when you are only 1 part in a million away from neutrality? So we can't do it. We can't get the gridding fine enough to get rid of the numerical noise in the calculation down to the 1 part in a million. To get it that fine, the gridding has to be so great that the machines will take eons to run. We have nothing that will work. So he quit in the middle of his contract. We have a lot of numerical simulation capability. That electrostatic code that I showed you with the particles going to the walls, that was a code developed by an ex-Sandia guy in Albuquerque. We had him modify it to some degree. And it's a brilliant code. It's wonderful. It was originally designed for particle beam accelerators. But that code only works in a collisionless regime. It's only for collisionless particles. But the minute we get beyond a few hundred nanoseconds, we have collisions. If we don't have collisions, we don't have expansion of the B field. So it's only the startup condition that code can help us with. Numerical simulation is great, but it has horrifying limits because of the nature of the physics of the problem. And we will use it everywhere we can. We can get bigger machines or parallel processors. That was the original game at DARPA. Have 5 parallel processors working directly on this system. It's going to be about an $8 million effort. Never had the money. We're waiting for it. Now, you ask about financing. We have no plans for financing. I've given up, as I say, on the government. Not that the government was bad, just the way the budgets are. Why do we run out of money? Because the fiscal year 06 budget in the Defense Department was cut. The R&D and Navy R&D was cut 26% in fiscal year 06 because we have to fight roadside bombs in Iraq. The Navy budget cut of 26% cut an entire line item out of the Navy. Advanced energy development, all gone. We were under that line item. So we had no money coming in FY06, and Admiral Cohen saved us just long enough to get those results. And there's no way in the current budget situation in the Iraq business and the current administration to get anybody interested in anything except 700-mile fences and Iraq wars and one thing and another. And that's what it is. And there's no way the DOE will ever support it, not until it's running in China, because it's a threat. It's a threat to this $2 million a day rice bowl. And everybody is pounding down the road toward ITER to be built at Cadarache, France. And this is the next big thing for the next 30 years. They can all do research and retirement on that. I don't see government doing it anywhere, any Western nation. That's why I limit the overseas nations to those people who are not partners in the tokamak program. But there are enough of them, and an average of 40 million a year. It can be done by a lot of different countries. And it probably will be if we don't do it. Now, do I have a plan for private money? No, I'm here by accident because Noel called me one day and said, "Why don't you come to Google and give a talk?" Well, I happen to know something about Google and its people and your stockholders, and I think it's got an interesting outlook, and you have a very exciting point of view and a very exciting way of doing things here that I haven't seen in a long time. And you have a lot of money, and if there's any serious interest in changing the world on a long time scale, it's not going to return anything in 2 years. This may be a place that should pay some attention to this. Obviously, we need an angel. There are a lot of people in this country who have multi-billion dollars who could fund this at lunchtime. I have no intention of spending my life running around talking to them all. I'm too tired. No. If somebody wants to do it, they'll figure it out. And if they don't, it'll be in print. It'll be everywhere around the world, and I'll give it away. We have the patents on it. Somebody will pick it up somewhere. China's a participant in ITER, 3%. So they don't want to be thought to be not members of the community. But China is at Hefei building some very interesting tokamaks of the kind that we were looking at 20 years ago, quite apart from ITER, that will beat ITER to the punch. And I think that we have a lot of people elsewhere in the world who don't have the same kind of mental constraints that we have in this country. And for all I know, that's what will happen. I would prefer we would do it in the United States with people like you who have vision and go power and are excited about things. And so would Jim Benson. We would like to see Space Dev and Benson Space Company take this thing over and maybe work jointly with whoever else partners with it and go for the space engines. As I told Noel, when I was 7 years old, my objective in life was to fly to Mars. It still is. And these machines can do it because they'll make space engines 1,000 times better than anything else. Single stage to Mars in 4 weeks. HTOL to Leo at $25 a kilogram. 76 days to Titan, one of the moons of Saturn. It's a very remarkable engine. I wish I had a plan. I could tell you what a plan would be, going to all the foundations and all the multi-billionaires, the people who SpaceX and all those guys, Elon Musk and Jim Bezos and those people, but it's too tiring. And I'm tired in that sense. I'm talking to people. And the problem is the fusion community is so old and so entrenched, you always run against them. And the immediate question you always get when you talk to people who are not personally themselves, do not personally themselves understand the curiosities of the physics and why it really will work, even though you can tell them it will. Either they believe you because they know you, and they know you don't lie to them, or they say, well, it sounds good, but I have to have it vetted by somebody, and they don't know where to go to vet it. And the first question you always get is, how come if it's so good the United States government isn't doing it? That's the first question. I've had that question in France and other nations. That's not unreasonable. The answer is very long and tedious, and it sounds like sour grapes, but it really isn't. It's just reality. In a private world, in a world of private industry, where people don't think like government, they can understand that. You do what you do because it's right, and it will work. You try it. That's what you do here, I think. Question? Yeah.
Anybody else try to reproduce the results?
No, we just published it for the first time in October. We have the only other people working in the field that I know of are at University of Illinois, George Miley, who's working in the Hirsch-Farnsworth regime with grids, and Jerry Kolsinski and Santarius up at University of Wisconsin, where they have been working on Hirsch-Farnsworth machines for a long time also. They're all stuck with the gridded systems. Nobody's trying to do the magnetic confinement thing, possibly because we held all the patents on it. But that wasn't stopping them from doing research. But I know George for 30 years, and I've known all these guys for 30 years. They're good guys. They just took a different path. They wanted to see if they could make Hirsch better. They haven't been able to. And there's a group in Japan doing something similar, Hirsch-Farnsworth machines. There's a man in Germany named John Zved who's building semi-cylindrical systems to make neutron sources for measuring paper thickness in paper mills, but that's not fusion power. That's making a diagnostic instrument out of it. It's like well logging. The PFN well loggers run on accelerated de-tritiated targets and make pulsed neutrons that go out into the oil fields and scatter back depending on the hydrocarbon content. And I know nobody who's doing this. That's part of the problem in the review committee, is that there's no group of people to turn to who have been working on it. Except people who worked on it 25 and 30 years ago. So,
why did you choose to publish in astrophysics, conference with physics or say like archive?
Partly because I'm a fellow of the International Academy of Astronautics, and partly because I'm a spaceflight enthusiast, and partly because the meeting was being held at a time which fitted my time schedule to submit a paper. I was going to go to Valencia and give the paper, but certain medical limitations on what I can do, so I didn't go. I just sent the paper in, and the people have it there. I hope to publish a much larger paper in a journal like Fusion Technology, but I haven't written it yet. It's a daunting task, I'll tell you, to try to figure out how to condense 11 years of work and about 100 internal technical reports. We've documented all this in reports to the government. We have huge numbers of reports. Trying to condense all that into a paper. I mean, I don't know. And who's going to review it?
We're coming up on, well, actually, we're a little past 3:30, so I think we're going to close things down. But anybody who wants to talk, please come up and chat. Well, Dr. Bussard will also be dining at Google this evening, so if anybody would like to join us, just come up. And thank you for coming.
Well, thank you.
And